All right, thank you very much for this nice introduction. My name is Tim Heulebruck. I am the product manager for Hyperspectral Imaging technology here at Stemmer Imaging, and I'm working here since 2015 as a product manager. This is my colleague.
Hi, I'm Gerhard Stanzel, sales engineer and technology specialist for Hyperspectral Imaging. So we work as a team, and yeah, Tim will start with our portfolio in hyperspectral devices.
Thank you very much, Gerhard. So for the next 15 to 20 minutes, I will be talking about the following topics. On an abstract level, I will show you what hyperspectral imaging can do. You will learn what our hyperspectral imaging portfolio is and what equipment is necessary for most, if not for all, applications. I will close my talk with a success story in the food industry before handing over to my colleague Gerhard Stanzel, who will present you our services on applications. So let's start right away. First, let's have a look at the evolution of machine vision industry. First monochrome imaging detectors were available already since the late 1970s or even the early 1980s. Digital CCD sensors are available since the 1980s, but machine vision was quite unknown back then. It did not take too long after the invention of CCD sensors to invent Bayer patterns and make digital color cameras very popular and available on the mass market. With stereoscopy and later then laser triangulation systems, we were able to detect three-dimensional properties of products in the production processes. But still, there are features that are invisible to the human eye, and that is where hyperspectral imaging plays an important role. It can make chemical features visible. Like you see here on that apple, you can see bruises which were not visible with monochrome imaging or not even with 3D imaging, because these bruises are just on the surface of the image. Getting further, now take a look at this bottle. Modern machine vision algorithms and modern machine learning algorithms may be able to detect that this is a bottle, but after extensive training and teaching, this would probably just be possible to detect that this is only a bottle, nothing more. But what if you want to separate the PEHD bottle cap from the PET bottle? Or what if you don't want the paper strip in your PET raw material because you get paid for mass and purity of the materials that you sort? Well, there you have the answer. Hyperspectral imaging or chemical color imaging helps you identifying these exact features reliably. You can even detect mixtures like the purple transition part between the bottle cap and the bottle, or the paper at the transparent back of the bottle. Now, where can we find applications like this as well? You can sort out rotten berries from your deliveries. You can inspect your packaging for impurities. You can sort minerals or plastics. In the pharmaceutical industry, hyperspectral imaging can check the ingredient complex of pills, and the wood industry can reliably detect wet parts, knotholes or resins on planks. Besides these applications, we have received many more requests from all kinds of industries, and my colleague Gerhard Stanzel will come to that later on. I will explain an application in the packaging industry or in the food and packaging industry in combination. So, what parts exactly do you need for a successful hyperspectral imaging system? You will need a sensor, a spectrograph, the heart of the hyperspectral imaging system. You will need a proper lens, and you will need an imaging station that is powerful, as well as powerful software, which is the brain of the hyperspectral imaging system. So let's start with a camera. There is a variety of vendors on the market from which you could pick your setup. We help you find the best one for your application. For the VNIR spectral band, we offer cameras like the Dalsa Genie Nano with a 5 GbE interface, or if you need even more speed and you can work with shorter cables, we can offer, for example, the GIGO series. For embedded camera systems, we can recommend the Alvium series with its USB or even MIPI interface for very high frame rates and data rates. In the sphere range, we can offer cameras from Xenix, like the Bobcat or the very newly released Wildcat series with USB 3 interface, or also cameras from Elite Vision from the Goldeye series, which is available through us, also with its very newly released Sony IMX sensors, which are sensitive in the range of around 400 to around 1700 nanometers. So you have the visible and the sphere range in one sensor. When it comes to the spectrograph, as I said, the heart of the hyperspectral imaging system, we offer the Specem V10E for the VNIR and the N17E for the sphere band. And in case your application requires something more special, we can also talk about Oem Designs. Obviously, this requires some business volume, because otherwise it's just not affordable, both for you or for us. Now we have a camera and a spectrograph, and you need a lens. Which one should you choose? In the Visneo, we strongly recommend Schneider color-corrected lenses, as they are affordable and have a very small focus shift over the wavelength. Keep in mind, different wavelengths need different focus settings, and hyperspectral imaging applications should stay the same for a broad range. For the sphere, we can offer this Cova HCSW series for most standard applications. For high-end applications which require more focus stability, we also offer Schneider Spheron lenses or the very new Cova HCSW series. And in case your application requires spatial measurement on HSI datasets, ZIL has some very good sphere telecentric lenses as well. Well, now you took the long journey and we have found a camera with a matching spectrograph and a lens, and maybe this work is not all necessary and all you can do and you can skip all this work by using the all-in-one solution, which is the Specem FX series cameras. We have the FX10 for the wavelength band 400 to 1000 nanometers and the FX17 for 900 to 1700 nanometers in our portfolio. Your advantage is the whole setup of lens, spectrograph and detector perfectly matched together. And you also have just one vendor for 3 hardware parts, which makes the vision hardware support a lot more convenient. Now that we have the imaging part of the system, we are still lacking illumination, right? Still most common is halogen illumination, which you can buy from us as well in various length and height configurations. However, increasingly popular are LED illuminations, both for visible, VNIR and sphere. The trick is to use the right LEDs and distribute them over the illumination in a way that an as homogeneous spectrum over the desired range comes as an output as possible. That is tricky indeed, and not many manufacturers are capable to do that properly. Also, the power still sometimes is not enough. But the advantage is clear. You get a huge variety of shapes and designs, but even more importantly, there is significantly less heat generation below the illumination. Here you can see some examples of light spectra from natural sunlight, or for example also the very new CCS natural white light illumination. Okay. Let's come to the software part. What can you buy there? We can offer you the CVB Spectral DLL, which can be used as a standard acquisition tool and saving NV cubes for the hardware, to the hardware drive. However, you sure want to do much more than just data acquisition, and therefore we have the Perception Park software. With the powerful Perception Studio, you can model and explore your data, while the Perception Core is for full inline processing tasks. If you have an application with a strong business volume, Perception Park also offers the development of certain apps which are tailored to your application, which are more cost efficient. Of course, most industrial applications require an industrial PC. The advantage is obviously the high power and freedom of configurations you get. We can look to get all these components for you and mount them together here at Stemmer Imaging. Besides IPCs, we also offer embedded platforms too. The NVIDIA Jetson platform, meanwhile, is a proven solution for hyperspectral applications and gets faster and faster with each generation. And you can either buy it as a bare board, or you can even buy a complete box from us. So now you have all the hardware parts and the software parts that you need to do your hyperspectral imaging application. But let's have a look at a success story. As promised in the beginning of my talk, let's have a quick look at this story. Bergader cheese is cheese of excellent quality and purity. However, there may be contaminants of cheese residuals in the heat sealing, and these can be transparent and under the printing, thus being invisible to the human eye. A hyperspectral imaging system reliably detects such contaminants. If you have such an application, do not hesitate to contact either us or Minibea directly, who are the integrators of this application. But Stemmer Imaging not only delivered the hyperspectral imaging system, but a full solution to the customer, including a monochrome line scan camera and a software for the image processing. Including here means a Teledyne Dalsa monochrome line scan camera, a Fujinon lens, a mid-opt filter, a bar lights for this, and also frame grabbers and a protective housing. In the food industry, you always have to remember that there are special housings needed. As I said, if you have such an application in mind that could be solved like this, do not hesitate to contact us. Especially do not hesitate to contact my colleague Gerhard Stanzel, who will now explain you how to get to these kind of applications quite easily.
So, thank you, Tim. Thanks for this nice overview about the portfolio, the hardware we can offer. Also thanks for leading to the next steps. So, how do we handle your inquiry, your application? And so therefore this slide, which shows the start, the inquiry, and also the end, which could be the life cycle management for your product, for your machine. Typically an inquiry starts with a certain task, a problem. I have this product, I have to inspect this or that features of the product, and that's typically the first contact point when customers are approaching us. We try to find the requirements of the application, so each product is a little bit different, each application requirement requires different setups and so on, a different field of view, frame rate requirements, also about resolution, the environment plays a role, there might be any mechanical restrictions in your machine, and it also depends on your capabilities. So are you already a hyperspectral professional, knowing kind of everything? Or have you just started and maybe even just started with machine vision? So no matter at which point you start or you are, or what is your application, get in contact with us. So that's typically the first step. And then most of the times it's also about samples. So the easiest step is if you can handle over a few samples, we can take them, go into the lab and have a first view at these products. And also hyperspectral is one technology, but there are a lot of other ones, and it might be solvable monochromatic or even with polarization, a totally different method. So this is what we would call a pre-feasibility, having a first look on your product, on your problem in the lab, get an idea of how to solve it, make a concept of a setup that could solve the task. That's part of a pre-feasibility. We test technologies and can already give you an idea about ballpark prices. So what would be the range I have to invest, and is it worth what I have to spend for it? This could even lead or end up with a first preliminary proof of concept. So we've seen this in your product, and it seems like it can be solved with this or that technology. A next step is typically a deeper feasibility, more samples, a deeper look on how it can be solved and so on. We verify the components that we selected in the first step, and make the final proof of concept with what we thought how we can solve the application. And then resulting of that is an advice from us based on the results we get with the technology we used. Then it can go into a system concept, and maybe also a discussion about is there any alternatives. So this happens quite often. We thought again about our product, and this or that would be another way to go with it. The technologies can be monospectral, dual wavelengths, multispectral systems, but also polarization, fluorescence, laser scattering beneath 3D thermal inspection, but also hyperspectral, which is our focus today. Hyperspectral can also be can give you the information on how you can solve your application, also monochromatic or with multiple wavelengths. So we will come back to that later with some examples. Then if everything is fine and all sides are happy with what we suggested and how we can solve the application, we go into a final system design. We fix the hardware and software. Might think about, are there any additional requirements we should take care of? Then it's also about housing, finding the right cables for your applications. So if you want to mount a camera on a robot, you should go with robot cables instead of standard ones. All these tiny details. And finally, it's a system or a subsystem definition we end up with. And of course, at the end, you might want to test the setup in your machine with your final customer, and this can be the last step to do a customer test. Beneath that, we also have other services and supports like system trainings. You might need an integrator. We can do manufacturing services, also modifications, calibrations. And I think a very important point is that we can go with system support. So not only for single components, we take care about the whole system, all that's needed for the application. And of course, it's good to get support for all the parts you acquired. Finally, it's also about lifecycle management. What happens when a device becomes obsolete, and so on. Having a look at applications. So this is a slide I made for our technology forum in 2019. So the times before Corona and COVID. And I picked out one of the applications about foreign body inspection because this is a relatively often asked question. How can we find this or that, anything that's not meant to be inside of our product? So Hyper, what is it good for? Foreign body inspection. This is a slide from the Rapid Alert System for Food and Feed from the European Union. We see some examples in which products these contaminations, these foreign bodies occur, but also different, beneath foreign bodies, of course, also other problems occur. Some of them can also be addressed with hyperspectral imaging. But for today, let's have a look on foreign bodies. The most ones are still metal and glass, even if they can be inspected relatively reliable with X-ray technology. And then it's already plastic fragments, polymers, pieces of plastics inside of your product. And the problem is often that the color might be very similar, so that they are just hard to find. Plastic pieces are not reliably detectable by X-ray because of their density. They have a much lower density compared to glass and metal, and therefore it's tricky or even impossible with X-ray to do that. You can detect polymers, plastic parts with hyperspectral imaging, But we are not looking through the whole material like X-ray is doing it. We're looking on the surface. The light penetrates a few millimeters, also depending on the product, but there are limitations that have to be kept in mind. Yeah, one of the examples I want to show is a real-world example that happened 2019. We have in Germany a page called Lebensmittelwarnung.de, so the pendant to what we've seen before from the European Union. And there was a warning. It's a screenshot of the page where the reason of the warning was that there were polymer particles, plastic particles on the pizza, white ones on a tuna pizza, which you might mix up with onions and so on. So it's a bit hard for the eye, and also therefore also for a machine vision system, for a traditional classic one, to find these objects. So this is an image of a prepared pizza. You might find one or two of the contaminants already in the image. Of course, I marked them here with the red circles so that you know these are all contaminant pieces. Some of them are easier to find and some of them really tricky, and I'm very sure that it's not possible to make a machine learning, a deep learning system being able to find this without the additional chemical information. So here's a close-up too, and I think you can see this is very hard to find. So going on, we made a record of the pizza with the contaminants with a Specim FX17. We used the Perception Studio to select the reference spectra and to make a first model. So this work typically takes like 10, 15, 20 minutes for the first step. And then on the lower slides, on the lower screenshot, you see the spectral signals of the contaminants and the ingredients of the pizza. So the final result image looks like this. Everything that's not meant to be on top of the pizza, no part of the topping is marked in red. Everything else is marked in green, and I think you can imagine it's relatively easy to analyze an image like that. Yeah, a short summary about the polymer topping of the pizza. So I'm quite sure it's extremely hard or even impossible to train a machine learning or a deep learning classification system based on RGB images. And especially as humans can hardly identify these parts. Yeah, the use of hyperspectral imaging reveals more information, other information, the chemical information about the objects instead of shape and color only. Yeah, these chemical informations are used to identify the foreign objects, and it's based on their chemical properties. Yeah, this makes it a lot more robust compared to other solutions. Yeah, the relevant information is mapped to colors. This is what we call chemical color imaging. Yeah, where we work together with Perception Park to enable this. And the resulting image streams can be used with standard image processing software like Sherlock, CVB, Halcon, whatever you want to use. And the Perception Park software is kind of translating the chemical information into these chemical color images. One of the limitations in hyperspectral imaging is still resolution and frame rate, because we have to make an image for a single line to get the spectral information. It's of course not as fast as standard line scan cameras. And you might come up with the idea also when having a look at the spectra that it could also work monochromatic in the shortwave infrared at around 1450 nanometers, where water is strongly absorbing. This could work quite fine for polymers, but if you also have other contaminants like a humid piece of wood or whatever, so when pieces are not dry but humid, then it will reach its limitations. Another example is minced meat. So we all know it, and also there sometimes it happens that polymer pieces find their way into the product. And this is also an example I took from Lebensmittelwarnung.de. So it's also a real world case, this happened. And it was about red polymer pieces in minced meat, which is also red. It's also interesting to see here the upper image is made with a mobile phone with a cold light LED illumination. The lower one was made with halogen, where the meat is looking more reddish, and but therefore also it's harder to find the red pieces. But it's even easier with hyperspectral imaging. As you're looking for the chemical information, you already see in the background the chemical images we made with the polymer pieces in red and the minced meat in green. Yeah, this is how the spectra look like in the shortwave infrared range. So the green plot is the minced meat. When you have some experience, you can also see, okay, fat information is playing a role around 1200 nanometers. Over 1400 nanometers, you have strong water influence, strong water signals, a strong absorbance basically. And this is how you can interpret the spectra. Red is the spectrum of the red polymer on top of the red meat, and blue is the tray where the meat is in. Yellow is kind of the mixture between the red polymer, which is under a thin layer of minced meat in this case. And I think you can imagine getting the green and the red plot together might end up with something like the yellow one. So this is also a basic concept of this chemical imaging, where your chemical information, if it's mixed, also your color information will be mixed in the final image. Yeah, then the question was, as the shortwave infrared has some advantages, but sometimes also some disadvantages, is it also possible to go in the visible near infrared range? So with a sensor system based on CMOS sensors, 400 to 1000 nanometers, in this range the chemical information is not that strong. And of course, you know, in the first 2/3 of the spectral plot, you will find mainly color information. So when we have a look at the green plot, which is the minced meat, you see a strong signal in the longer wavelength, so roughly at the middle of the spectrum, which is then the red color we see as humans. And then it goes on, and at a certain wavelength, almost at the end, around 970 nanometers, is also water information, less weaker compared to the shortwave infrared, but there is information called the second overtones. Red is again the polymer on top of the red meat, and blue is the tray, which is green in real world. And there are differences in the visible range. We have the second overtones in the NIR range, and it's a mixture of color information and less strong chemical information in the NIR. So chemical information is less stronger. Nevertheless, you also see already in the visible range that the red of the meat is different from the red of the polymer, even if it might look similar when looked at it with the eye. Yeah, then a method that's quite often used is taking a first derivative of your signal, so that it's less about the absolute values and more about the changes in the signal. So this is a first derivative that was used for a model. Also there you can see green is the meat, red is the polymer, blue the tray, which is not inside there, but the gray plot is the mixture between both. Yeah, so far for the food industry, another example in materials technology, right now in development kind of, because this is currently not an approved method of building a house or making construction parts. It's about the development of cross-laminated timber walls with glued-in ultra-high performance concrete lamellas. This is a dissertation that somebody's writing at the moment, Mr. Oberndorfer. Thanks for your support. So we made the spectral cubes in our lab together with him, and he made the further analysis. It's about gluing wood in concrete, which is not that common already. Typically you use classical mechanical interconnections at the moment, but it could be a method of the future, and I think you can imagine it's just faster and easier to glue two things together. The question is, when you do a shear test, what is failing? Is it the glue, the wood, the concrete? And that's about this study, this dissertation. As always, or kind of always, we first took the spectral signals of the objects. So we scanned the two halves of the sheared object. On one hand the concrete, on the other hand the wood. And that's the spectral signal. So concrete doesn't have strong spectral features, but with the glue on it, you see on the top both plots that it's already looking different. And then for the timber, the same on the lower plots. Again, we took the data in the perception studio, we made a model, so we colorized the chemical information to be able to process them further on with a different software. Here it's green for the concrete, blue for the timber, and red for the parts which have some adhesive on them. Yeah, this is the analysis of the resulting chemical color images, which were done by Mr. Oberndorfer to find out where has which part failed. So was it the timber, was it the adhesive, was it the concrete? Yeah, and let's see if we will find this technology later on in real buildings and see this getting approved. Finally, we come to two short examples where here it was about a transparent lubricant on a polymer part. Green is the polymer part only. Red is it with the transparent lubricant applied on it. And we see on the red plot there's a unique absorbance band of the lubricant. And this is always a signal where you say, okay, it might work also monochromatic if finally the contrast is high enough. But it's giving you a sign, so this could be possible to solve easier. So here hyperspectral technology brings you the basic information on which wavelengths you might look like, what is the right wavelength band, and then being the step on going monochromatic with a shortwave infrared camera, which could be a line scan or area scan, making the use a little bit easier. Yeah. So we used this narrow band, we found a suitable monochromatic filter, a bandpass filter in the shortwave infrared and made the test. And then within the discussions with the customer, we finally come to the point, but it's applied hot. So then you ask, wouldn't it be possible to also do it with a thermal imaging solution? And finally, we also tested this. And then we get in discussion with the customer, which is most suitable and what could be done to solve it finally. Another application where it was really necessary to go with hyperspectral was a thin layer of glue on a foil, where you see here it's already the first derivative of the spectral signals. There's only tiny differences in certain wavelength areas, and this also with the intensity spectra, it just wasn't possible to solve this in a monochromatic or a more easy way compared to hyperspectral. Yeah, finally a short conclusion and a bit of an outlook. So hyperspectral imaging enables chemical information as well as more detailed color information to be used. And it's about your product and your produce, and the possibilities are quite manifold. Depending on the application, a monochromatic or also a multispectral approach can be an option. We offer all these technologies, so we are not depending on a single technology level. And typically this comes with the benefit of higher resolution and higher frame rates. As always, it's always good to keep it simple if it's possible, but also you should keep in mind that there might be a further or a future use. For example, in the recycling industry, you never know which polymers will come in the future, and the recycling machine should do the job for 10 or 15 years. So we always have the pros and cons, but get in contact with us to discuss them, to discuss your application with us, and to find a solution to your application. Currently happening, so it's a bit a view on what is happening now and what will be coming in the next months or within the next years. There's right now, similar like we've seen it with normal cameras with the EMVA 1288, the standardization is also happening for hyperspectral, multispectral cameras at the moment. We see a constant improvement of LED-based hyperspectral illuminations, both in the visible near-infrared as well as in the shortwave infrared. And we also see embedded coming into the hyperspectral devices, similar to embedded cameras like we've seen it before for standard vision applications. It also comes with hyperspectral apps, like Tim already mentioned. So if we can break it down to a single application, for example, getting a true color information out of your visible spectrum, this can be reduced to a specific application and offers also more possibilities. We see new sensors coming out, also like Tim already mentioned, the new Sony sphere sensor for the vis and sphere range, but it's also new sensors from Hamamatsu coming out, colloidal quantum dot sensors and so on. So we try to stay on top of what's happening in the development also. And another point is customer-specific multispectral cameras like the Chai FlexEye, where you can define the wavelength bands you need together with us and Chai to define your specific application-specific camera. So, thanks a lot so far for my part. I hope it was something interesting for you. Hope you enjoyed this webinar. And thanks a lot for watching.